it said this data can be scaled through a normalized length scale, Hopkinson scale, R star. Red is what I put that in. R star is a scaled ground distance. R star is equal to R divided by W to the 1/3 power to get the scaled. So I'm not gonna talk much here because we're gonna talk scaling, Hopkinson scaling law next month. So something like some pressure, for example, for the model is lambda to the P prototype. Best bet is I should use just the L. As I mentioned, Hopkinson's scaling law, one of three assumptions is lengths scale linearly. This is what it said. This is lambda is a scale factor, Hopkinson scaling factor. L is a length in prototype. This is a length in the model. Okay. So this is you have to. This is a basic assumptions. Okay. And then what about the W to the M is equal to scale factor W to the prototype. This is what you're looking for. W here is the mass in the model, mass of the model. This is a mass of the prototype, something like a mass density of the prototype. This is, so let's say mass. So here's a prototype is for the mass. What's the unit of the mass? Mass is volume times what? Mass density, right? Volume times mass density. Mass density is a constant. One assumption, this is one. I'm not gonna giving you a full lecture on the Hopkinsons. So same material. Same material, second assumption. What does it mean, second material? Mass is the same. Mass in prototype is same as mass, okay? Mass density, rho is the same. Rho naught is equal to rho m is equal to rho p. So this is just a mass of the structure, so which is a volume times mass density. So which means here the Vm times rho naught, right? Because it's the same. Rho m is same as rho naught. So this is a Vp, right? Scale factor, Vp times rho p, but it's the same material. This cancels out each other. And here the Vm, when you just look at the unit, this guy is length model cube. This guy is also length. I'm sorry, not this guy. This guy is length prototype cube, just the unit is concerned. So if I rewrite over here, length model cube is equal to the prototype here, scale factor times LP cube. Rho is all canceled up. So now you can just drop this guy. So this is what this result is. But going back to here to get the same idea, so Wm is equal to, that's R, yeah. Wm is equal to something Wp. So now when we look at this guy becomes this, which means, let's say this guy is lambda, maybe underscore. So this is Lm is equal to lambda underscore Lp. So what I'm saying is, in the Hopkins scaling law, the scale factor, Hopkinson's scale factor, this is basic assumption. This is what the basic assumption is go back right here. This is, when you go back, it just comes right back in there. So over here, W is mass. Okay, this is for scaled, unscaled. This is scaled. So this is W to the 1/3 is W is the L cube. So to the 1/3 power, so back down to L. What does it mean? It's scaled, and prototype has the linear scale factor. So this is a length scale, and this guy is a mass scale, right? So which mass is rho v. Rho is invariable. Same mass density between the prototype and the model. So this becomes really L. So length is really L. So here did not say much, but just shows like that. A lot of things shows like this. So don't confuse it. And when I cover really Hopkinson's scaling for an hour in November, then I think you will see all in and out, okay? That's what you're gonna see that. Over here, just accept as R star is equal to R over P to the 1/3 power. R is ground distance from the center of the explosive, okay? So capital W is the mass of the explosive source. We'll stop there. So here is scaled distance versus side-on peak pressure. TNT method, one of the methods, the idea is try to predict for the case of gas explosion. I read this, but what they are claiming here is don't use this TNT data unless the pressure is higher than 1 bar, because high explosive result is not good for low pressure. So that's what it just mentioned, okay? So then they use a yield factor. It's all modifier. So I don't want to bother you much on that. And talking about the drawback for the TNT method, they use the word TNT equivalence method. You don't have to pay much about it, okay? So this is what. And another methodology that Vandenberg in 1985, he also proposed the multi-energy method, another method, but using the chart and all that, but I don't really much pay attention as we're looking into gas explosion, the handbooks. So you can just look at that, okay? And this is worth to make a notes on this. This is a gas cloud over here. This is a gas cloud here. It could be a tremendous volume. You see that Busan kind of the leak. It doesn't just cover one small area of the whole factory. It covers the whole village. So everything dies within the whole village. This is what the gas cloud is. And within the gas cloud, gas explosion could occur in two different areas. 3 or 4 different areas. When you draw the shock time history, let's say this point, this could be just a general, okay? So this occurs first, which means closer to area A first here. Then from area B comes from the second. So 2 different gas explosion could occur. So this is one by the explosion due to the area A, and this is due to area B. So you can just use that sort of the assumption. Answer is okay. Depend on the distance between the area A or B, and this you can combine to 1. Depend on the condition, how far away this is. But this is all within the gas cloud. This is worth to make a note. In the detonation for the high explosive, it's not just simple like this, but for the gas explosion, this may be good enough. This scales of the experiment, same thing coming up, and not much worth to talk about it. The numerical method, everything is boiled down to flags. So we'll wait until the end of next week to hear the flags. But flags here, this is published in 1985. So they are talking about the flags and flags 3D. Nowadays, this is all combined as flags. There is no such a thing as a flags-3D. The flags and microflags, they delete for distribution, and only flags available. And predictability using the flag itself is not absolute God. I want you to know that. This is a prediction. Prediction, everything is not 100% correct, or result may not be very close to the actual result, but that's the best predictions. So it looks like in the industry they are using the flag all the time. That's what my understanding is. That's what, when you getting into the plant design, chemical processing plant, things like that, then you will end up learning the flag. But if you are not involved on that gas explosion, you don't have to, but the knowledge itself would be sufficient. Don't be frustrated. That's what the nature. This reflection of this is, I mentioned briefly already, free field blast wave. This is very interesting, but it shows the propagation of a wave, And it shows all different kind of the wave. Shock wave, this is side-on shock wave, or side-on wave, or side-on gas explosion wave. Is a building, is an obstacle, or this could be any ocean systems structures. And this is a building like rigid, and when it hit it, then it has to reflect. So this is a part of the reflection wave. And the shock wave, incident shock wave, is moving along here. It doesn't stop. And the reflection part, the varying point has to be continuous. So as reflection occurs, this part will move on. So you can visualize this guy keep moving opposite direction, but the portion of the wave will move on. And at this point, when wave move down to that point, this sort of the closure wave is happening. This is called the diffraction wave. D-I-F-F-R-A-C-T-I-O-N. Diffraction wave is wrap around. For example, in the dark evening, when you put the flashlight along here, if you stand down here, you can feel this is not total darkness, but you can really see the things around. This is due to the diffraction wave. Diffraction wave, and this is all keep moving on, okay? So in terms of the pressure value, so it said here is a factor of 2. Factor of 2 is the pressure experienced by this wall is a factor of 2 because it's pretty rigid. And down here, this is down along the surface, it said 1.4. In the reality, theoretical sense, it's going to be a factor of 1.0. But nothing is perfect. So if it tilts a little bit, that's really a factor of 2, but they just estimate saying factor of 1.4. Nothing is really perfectly perpendicular, parallel to the wave, so they estimate is not the 0, it's a 0.7. So this is what the reality is, okay? Okay, now it's done. And guideline, I put the first paragraph. You know, it looks good, but it said you need to know the source strengths, but you don't know the source strengths. That's a problem. Okay, so up to chapter 7. I usually go one chapter at a time, and Wednesday I'm going to cover the chapter 8. Chapter 8 is what? That's response of the structure. 400 pages thick, try to cover in 5 pages. As I feel to myself is insane, but we'll move on. But you, most of you took the vibration class, yes or no? Yes. Vibration class? Yes. Yeah. So, and the structure dynamics, you have a taste of structure dynamics. So chapter 8 is really little bit, 0.5% of structure dynamics is what it covers. I'll just, skimming, then move on, okay?